Hello guys, hope you have been having a very lovely day. In this video, we'll just see how to sketch the root locus when a transfer function is given to us. So all you'll need is just a graph sheet, a normal graph sheet, and some rough work, and your question. So there are different cases for when you're giving complex poles, when you're given complex zeros, and the cases vary because there are a few complications that will arise. But let me start with the most simple example I can, and let me explain you the complicated versions in my other videos. So I'm taking a very simple transfer function. G of s is equal to s into s plus 2 into s plus 4. So this is my transfer function that is given. I need to sketch the root locus for this transfer function. So to sketch the root locus, don't get confused. All you'll need to learn is a few rules. First, find out poles, zeros. Next, find out poles minus zeros. That is number of poles minus number of zeros. Next, find out angles of asymptotes. Let me just tell you, these asymptotes are nothing but a few guidelines which will help us sketch the root locus. So we draw our root locus along the asymptotes. So to find out the asymptotes, you'll actually have to find out the angles of asymptotes. And to know where the asymptote starts from, you'll need to find out the centroid. Don't worry about anything. I'll be telling you each and everything in this video. So you need to find out the centroid. And after you have found out all this, you need to find out breakaway or break-in points. A breakaway point is that point on the real axis where the root locus will separate itself from the axis and go to infinity. That is a breakaway point. Whereas a break-in point is when a root locus comes and meets the axis. That is a break-in point. So we need to find out all these things when we are given a transfer function to sketch a root locus. So apart from this, there are a few things that are added, and also we'll have to find out where the locus meets the imaginary axis. But apart from this, when we are given complex poles, that is, if you look at this transfer function, it is s into s plus 2 into s plus 4. So the poles are 0, minus 2, and minus 4. But just imagine a case where you cannot further factorize the denominator or the numerator. For example, I have s squared plus 4s plus 11 or something like that. Then in that case, I'll have to find out a few more things. That is when the root locus becomes more complex. So in this example, you won't be finding out those. I'll definitely do that in my next video. So those are finding out the angle of departure and the angle of arrival. So these are two things that are going to be added to your sketching and to your work when the root locus you have to find out is of a transfer function that has complex poles or complex zeros. So keep these 8 things in mind when you're sketching a root locus. The first thing is find out the poles and zeros, then find out number of poles minus number of zeros, also denoted by n minus m. Find out the centroid, find out the angles of asymptotes, there is a formula for that, and find out the breakaway and break-in points, and find out where the root locus meets the imaginary axis. So with these points in mind, let's get started with our first example where our transfer function is g of s is equal to k by s into s plus 2 into s plus 4. So let me just start from here. So I'm writing the transfer function again. So you're gonna do this along with me, right? So what are the zeros of the transfer function? Is there any s plus or s minus in the numerator? So there is no zero for the given transfer function. So number of zeros is equal to 0. So now coming to the poles of the transfer function. The poles of the transfer function are the s minus 0. So 0 is one pole, s plus 2 is one more root of the characteristic, that is the denominator. So minus 2 is another pole, and s plus 4 is another term. So minus 4 is another pole. So we have 3 poles. So number of poles is equal to 3, and the number of zeros is equal to 0. We have the poles, that is 0, minus 2 and minus 4. So now we need to find out, we have found out the zeros and poles of the transfer function. Now let us find out n minus m, which is the number of poles minus number of zeros. So 3 minus 0 is 0. So once we have found out n minus m, we need to find out the centroid. The centroid is nothing but sum of poles minus sum of zeros by n minus m. So what is the sum of poles? Sum of poles, that is 0 plus minus 2 plus minus 4, that is minus 6. So sum of poles is minus 6, and sum of zeros is 0, because there are no zeros, the sum of zeros is 0. And n minus m is 3. So minus 6 by 3 is minus 2. So the centroid is minus 2 comma 0. Whatever comes, the centroid lies on the real axis. So our centroid is minus 2 comma 0 in this case. So n minus m is not just n minus m is 3. I'm extremely sorry, terribly sorry, my bad, but I wrote it down right here. So n minus m is not just an indicator of number of poles minus number of zeros, it is also an indicator of the number of lines going to infinity. So if you remember, in the root locus, the branches of the root locus, they even go to infinity. So n minus m gives us the number of branches of that root locus that go to infinity. So if n minus m is 2, it means that 2 branches will go to infinity. If n minus 1 is 1, only 1 branch goes to infinity. If n minus 1 in our case is 3, so 3 branches will be going to infinity. So now we have found out the number of poles, number of zeros, centroid, and also 3 lines going to infinity. So number of asymptotes will be equal to 3, which is the number of lines going to infinity. Now we know the number of asymptotes. We need to find out the angles of asymptotes. So angles of asymptotes, let me take that as theta d, is equal to theta. Let me not take a d, because you might get confused when you find out the angle of departure in my next video though. Let me take just theta. Theta is equal to 2q plus or minus 2q. So theta is equal to 2q plus 1 by n minus m into pi, where pi is 180 degrees. So this formula is very simple. Theta is equal to 2q plus 1 into pi by n minus m. So in our case, the number of asymptotes are 3. Excuse me. So you will start with q is equal to 0 and proceed till n minus m. So you're going to take till 3. So you need to find out 3 angles. So in the first case, one angle theta is equal to, when 2q plus 1, I'm substituting q is equal to 0, which means 1 by 3 into 180. That will be plus 60 degrees. Plus 60 degrees. So this is for theta when q is equal to 0. Now I'm gonna take q is equal to 1. Then theta is going to be 2 plus 1, that is 3 by 3 into pi, which is 180 degrees. So 180 degrees. Now I'm gonna take q is equal to 2. Now q is equal to 0, 1 and 2. Is that so we have a total of 3 q values. So this is gonna be my last one. So when q is equal to 2, theta is equal to 2 into 2 plus 1 by n minus m is 3 into 180. So 4 plus 1, that is 5 by 3 into 180. So 5, 3, and that goes by 3, 6 times, right? And that is going to be 5, 6, or 300. And I think I can write this as minus 60 degrees. Yes? Yes. So my third one, when q is equal to 2, I got the angle minus 60 degrees. So you might actually ask me why, how you taking the angles of asymptotes, where exactly will you draw these asymptotes? Now, if you have not forgotten, we have found out a centroid in here, which is minus 2 comma 0. The purpose of finding out the centroid is to start our asymptotes. So our asymptotes are going to start from the centroid and move with angles of plus 60, 180 and minus 60 degrees. So along these lines our root locus is gonna lie. So it is also important that you draw a model root locus before actually jumping into your graph sheet. So I'll just turn this over and let me put this here. I'll draw freshly. Right. So let me draw a small model root locus. This is 0. Mark the poles with an X and the zeros with an O, with a circle. Since we have no zeros, let me not mark them, but let me mark the poles. They are 0, minus 2 and minus 4. So these three are my poles and I have no zeros here. And my centroid is also minus 2 comma 0. So this is where my asymptotes are going to kick off. So as we know, the angle of one asymptote is plus 60 degrees. Use a protractor, I'm not using one. That is plus 60 degrees. This is the first asymptote. And the second asymptote is 180 degrees, which is the real axis itself. So let's now draw another one there. And the third angle of asymptote is minus 60 degrees, which I can draw like this. So now I have the asymptotes, the centroid, the poles all marked on the root locus model graph sheet. So what I need to do now is to find out what part is actually present on this root locus. So how do I know which part of the real axis is a part of the root locus? So take any test point. You can take minus 4, you can take minus 3, minus 2, whatever. Any test point. If to the right side of the test point you have taken there are odd number of zeros and poles, then that part of the real axis is a part of the root locus. So if you're taking the test point as minus 5 or minus 6, then to the right side there minus 4, minus 2 and 0. There are 3 poles. So the number of zeros and poles is odd. So if the number of zeros and poles is odd, to the right side of that particular test point, the real axis is a part of the root locus. So if you take any test point to the left side of minus 4, the number of poles and zeros to the right side is always odd. So the whole real axis to the left side of minus 4 is a part of the root locus. I'm just brightening that part. This is the second, first or second branch going to infinity. So 180 degrees asymptotes, your work is done. So now take minus 4. To the right side of it, the number of poles and zeros is even because minus 2 and 0, there are only 2. So since it is even, this part does not lie on this part of the real axis, is not a part of the root locus. Now take minus 2. To the right side of minus 2, there is 0, a single pole. So the number of poles and zeros to the right side of minus 2 is odd. So minus 2, 0, this part is a part of the real axis. This part of the real axis is a part of the root locus. Now we need to find out how the root locus branches are actually going to take off. Now we have found out everything we have written down here except the breakaway and break-in points and also the imaginary axis meeting points. So to find out the breakaway and break-in points, we need to find out the closed loop transfer function. So in the question we have been given k by s into s plus 2 into s plus 4. We need to find out c of s by r of s. So c of s by r of s is equal to g of s by 1 plus g of s into 1, because assuming it is unity feedback, when there is no feedback given in the question, assume it is a unity feedback. So now find out the closed loop transfer function. Because this is a simple step, I did it myself, I paused it. You can have a look. So g of s is k by s into s plus 2 into s plus 4 by 1 plus that, and then both these common denominators, they get cancelled, and the final closed loop transfer function you're gonna get with the given open loop transfer function with unity feedback is c of s by r of s is k by k plus s into s plus 2 into s plus 4. So to find out our breakaway and break-in points, we are going to use the characteristic equation k plus s into s plus 2 into s plus 4. So k plus s into s plus 2 into s plus 4 is equal to 0, equated to 0. So what do you get? K plus s square plus 2s into s plus 4 is equal to 0. So once you get this part, find out, see that you will find out the value of k from these in terms of s. So the value of k is going to be minus of the whole thing, s cube plus 4s square plus 2s square plus 8s. That's right, isn't it? So which is equal to minus of s cube plus 6s square plus 8s. This is the value of k. To find out the breakaway points, we need to find out the roots of dk by ds. So dk by ds is you're gonna try. This is simple. Just you have this s cube plus 6s square plus 8s. So you will have 3s square plus 2 6 12, 12s, so 12s plus 8s, so you can just write that down as 8. So this is dk by ds. You need to find out the roots of this expression now. So equating this to 0, equating dk by ds to 0, you will get 3s square plus 12s plus 8 is equal to 0. Don't bother about the negative sign, you have equated to 0. So equate dk by ds to 0. Only then you will get to know what the breakaway points are. So from this I have found out s to be minus 0.367 and 3.63, not to waste time. So after finding out both the s values, remember not both the values are the breakaway points. You need to find out how. Take 3.63 for example, 3.63, and look at your model root locus. Is 3.63 which is a point on the real axis, a part of the root locus? No. 3.63 lies somewhere over here, and that part of the real axis does not lie on the root locus. So 3.63 is not a breakaway point, whereas minus 0.367, which lies somewhere in here, somewhere in here it lies, minus 0.367, it is a part of the root locus. So minus 0.367 is your breakaway point. There is another way of testing if the given root of dk by ds is your actual breakaway point or not. All you need to do is substitute that value in your k equation, in the equation that gives you k. If the result you get is real and positive, then that is your real breakaway point, and it is also a part of the root locus. So this is how you find out the breakaway point. After you find out the breakaway point, you need to find out where exactly these points intersect the imaginary axis, where exactly these branches will intersect the imaginary axis. You cannot draw them blindly, right? So now we need to find out points of intersection of imaginary axis. Imaginary axis, points of intersection. So for this, I am going to take the characteristic equation. This is my characteristic equation. This one is more simplified. So if I send this whole term this side, I'll get a positive. So I am going to take the characteristic equation, which is equal to s cube plus 6s square plus 8s plus k is equal to 0. Remember which characteristic equation? We have found out the closed loop transfer function of the given transfer function. For that, we have this denominator, that is my characteristic equation. So now I have my characteristic equation. To find out the point of intersection on the imaginary axis, I am going to put s is equal to j omega. This is the substitution that gives you the point of intersection on the imaginary axis. That's it. So if I am substituting this, j omega cube plus 6 into j omega square plus 8 into j omega plus k is equal to 0. So now I can write it as minus j, I'm gonna simplify this. I'll write it whole, j cube omega cube minus 6 omega square, because j square is equal to minus 1, plus 8j omega plus k is equal to 0. So now what I'm going to do is equate the real parts to 0 and the imaginary parts to 0. So the imaginary parts are these two. So minus j, because okay, so minus j cube is minus j. So I'm gonna write it as minus j omega cube plus 8j omega is equal to 0, which I can take omega common out of this, right? So minus j omega, if I'm taking j common, this is not gonna come. So right, so minus omega square plus 8 omega is equal to 0. So I've removed j, I've eliminated j out of it. So what I'm going to get out of this is omega square plus 8 is equal to 0. So because I have eliminated it, because I've eliminated omega and I've also eliminated j, I'll have minus omega square plus 8 is equal to 0. So omega square is equal to 8, and omega is equal to plus or minus root 8, which is equal to plus or minus 2.83 I. So this is my omega value, and now This is where the points are going, this is where the root locus points are going to meet the imaginary axis at 0 comma 2.83 and 0 comma minus 2.83. Now I'm going to also find out the critical value of k. This is however optional and you need not find it out if it's not asked. So now for that I am going to equate the real parts to 0. Minus 6 omega square plus k is equal to 0. So now k is equal to 6 omega square. So I have omega square is equal to 8. So 6 into 8. So k's critical value is 48. This, however, we are not going to use in our part of construction of the root locus. All we need is this intersection of the points, which is 0 comma 2.83 and 0 comma minus 2.83. So these are the 2 points where the root locus is going to meet the imaginary axis. So I'm going to mark them here. This is 2.83 and this is minus 2.83. So as we already know, the breakaway point is minus 3.67, and so mark minus 3.67 here, assuming this is minus 3.67. See that you draw along the asymptotes and touch the point 2.83 here, and that goes to infinity. This is one branch of the root locus. Another branch of the root locus also starts from minus 0.367. It breaks away from the real axis from that point and meets minus 2.83 here. So this is the model graph of the root locus, and let me now sketch this same thing on this graph sheet. So this is my graph sheet. I have marked the readings to a scale of 1 centimeter is equal to 1 unit on this graph sheet on both the real and imaginary axis. So always while drawing the root locus, even on the graph sheet, these values of your rough work are not just enough. Also keep beside you your model graph sheet. So as you already have, from minus 4 there is a branch going to infinity. So just darken that branch. So that is the first part of the root locus. From minus 4, which is a pole, minus 2 is a pole, 0 is a pole. From minus 4 it's going to infinity. So darken that. Now you have asymptotes at 60 degrees. Please use a protractor. I am not using a protractor. 60 degrees and minus 60 degrees. 60 and minus 60 degrees. And the breakaway point is minus 0.367. So minus 0.367 is here. So minus 0.367. And the points of intersection of the imaginary axis 2.83 and minus 2.83. So 2.83 is here and minus 2.83 is here. So starting from the breakaway point, draw lines along the asymptotes such that they meet the imaginary axis at the required point, and it goes to infinity. And the same thing with the other half, and it goes to infinity. And minus 2 and 0, this is also a part of the root locus. So now tell me, what is the root locus in this whole picture? This is the root, this is part of the root locus. 0 to minus 2 to 0 is part of the root locus. This line is part of the root locus, and this line is part of the root locus. And remember, draw perfectly and see that you don't get more curves and all, because the root locus is always symmetric along the real axis. So this is how you draw the root locus when you have no complex zeros and poles. For a complex zeros and poles, I'll be making another video. Hope this one helps you, and if you have an exam tomorrow, all the very best. Thank you and have a lovely day.